technically there are three types of beta decay. So the first, sometimes they're called beta negative decay. So beta negative refers to electrons. This is electron emission. Then you also got positron emission, so or positron decay. So the last type is electron capture. So again, these are all part of the table on your handout there. So the three different types of beta decay, they all involve a beta particle in some way. Notice an electron still is referred to as a beta particle. So the first type is beta decay. So in beta decay, it's called electron emission. So an electron gets emitted from your parent nucleus. So it wouldn't be the most likely thing to happen with thorium, but we can use it as an example just to highlight what exactly is going on. So if thorium-232 were to undergo beta decay, again, being electron emission, something's emitted as a product. You might see it again written either as a beta or as an E for electron. Either way, they're synonymous. So what would be the mass number of our daughter nucleus?
232.
So what would be the atomic number?
89.
Would it?
Oh, I'm sorry, 91.
There you go, 91. So what's atomic number 91? Sure you do.
PA.
Which is called what again? Protactinium. Yeah.
Why would you, because the Z is the charge, it's not necessarily the number of protons, it's the charge?
It's a charge, yeah. So we often think of it as the number of protons in nuclear chemistry, but for some of these other particles, it's more generally just the charge.
Okay.
All right, if you look at your result, so to see what your result is, it's often convenient to think of a neutron. It's not really what a neutron is, but it's often convenient to think of a neutron as the combination of both a proton and an electron combined together. That's what a neutron, makes it easier to kind of figure out some of these processes. So take a proton, what's the charge on a proton? Plus one. Electron.
Negative.
And if you put them together, what's going to be the overall charge?
0.
0, it'll be neutral. What's the mass of a proton?
0.
A proton?
Oh, 1.
1. An electron?
0.
0. If you put them together, what will be the total mass?
1.
So we have a total mass of 1, and our charge is neutral. That is the same as a neutron. So that's why it's functionally sometimes convenient to think of a neutron as being a proton and electron combined. So if we notice, if you eject an electron out of your nucleus, so let's say you've got this neutron, it's a proton and electron combined, and you eject the electron outside the nucleus, what's going to still be left in the nucleus? A proton. And so functionally, this electron emission is the net result of turning a neutron into a proton. That's the net result. So if we look at positron emission, so again, positron emission, thorium-232 might not be the most likely candidate for positron emission, but we've been using it all the way along. We're going to use it again just to give an example. So if we do positron emission, again, it could be written as an E or as the beta symbol. I'll use the beta here just to show both. Mass is still going to be 232 for our daughter nucleus. What's going to be the atomic number of our daughter nucleus? 89 indeed this time. And what's atomic number 89?
AC.
What is atomic number 89? Where am I missing it? There we go.
Radon. No. How do we... Oh, sorry. Minus a positive number, minus a negative number.
There you go. All right, so that's positron emission. If we look at electron capture in the same breath, so electron capture, notice this is the only one that's not an emission. So what actually happens is an inner shell electron actually gets taken into the nucleus, captured, so to speak. So an electron is actually a reactant, not a product. This is the only one where you've got this particle as a reactant for these spontaneous routes of decay. So what's our product going to be in this case then? What's our daughter nucleus going to look like? What's its mass number?
It's going to be 89.
Mass number.
Oh, I'm sorry, 232.
Cool. And atomic number?
89.
Notice the same net result as our positron emission. So positron emission and electron capture, whether you get rid of a positively charged electron or take in a negatively charged electron, it is the same net result. And that net result is exactly the opposite the exact opposite of what we saw with electron emission. So electron emission turns a neutron into a proton. So if we focus on electron capture for a minute, so if I take and capture an electron and bring that into the nucleus, that electron's going to combine with a proton to form a neutron. And so the net result, it turns that proton into a neutron. At least, again, that's not technically what happens. It just makes a convenient way to remember the net result. So both positron emission and electron capture functionally convert a proton into a neutron. Okay, so we talk about which nuclei are likely to undergo, so either electron emission, so versus positron emission or electron capture. So why would you want to turn a neutron into a proton? So, well, you have too many neutrons and not enough protons. So if you have too many neutrons and not enough protons, that means your N over Z ratio is too high. Which means you are above the belt of stability that we talked about earlier. So why would you want to convert a proton into a neutron? Because you've got too many protons and not enough neutrons. So your N over Z ratio is too low. So you're below the belt of stability on that graph we drew earlier. Cool, one thing to note about beta decay. Whereas technically these are all examples of what is called beta decay. So however, if somebody talks just generically about beta decay, they're just like, oh yeah, did some beta decay the other day. So they expect you to know that if we just say beta decay, and we don't specify which of these three we're talking about, they're always, always, always referring to electron emission. So electron emission is technically just beta decay. So if I want to talk about positron emission, I have to say positron emission. If I want to talk about electron capture, I have to say electron capture. But if I want to talk about electron emission, I can say electron emission, or I can just simply say beta decay.
Next time I want to talk about it, I'll know.
So last but not least, for your last route of decay, it's gamma decay, or gamma emission. So and again, gamma emission usually doesn't happen all by itself. It usually follows a different nuclear process happening. So when a nuclear process results in a nucleus being in the excited state, it may release a bunch of energy to go to the ground state. We're picking on thorium here. We're going to pick on it one more time. So if thorium undergoes gamma decay here. Since gamma decay is gamma emission, where's the gamma ray going to show up?
In the product.
Yeah, product side. So we got a gamma ray. And what's the daughter nucleus going to look like?
Same.
Exact same. Cool. And again, there's no easy way to predict who might undergo gamma decay. So again, it's usually accompanies other nuclear processes, and it's just nucleus excited state dropping down to the ground state, giving off a bunch of high energy light.
So is that, like earlier when we were talking about the excited state and ground state of the electron, and you said the asterisk may indicate that it's in an excited state.
Excited
Is this
state.
what you're talking about as well? Like that thorium might be in an excited state, now it's going down to a ground state? Or
So potentially it could look like this, or technically any nucleus about to undergo a nuclear process, any of these nuclear processes might be written with an asterisk. So it's usually just identifying a radioactive isotope that's going to decay. So you might see it as either way. All right. So if you notice, how many of these processes result in a loss of mass? Not mass number, just mass, being that they're all nuclear reactions.
None of them.
Again,
just the
I'm sorry, alpha
decay?
decay.
so again, not mass number, just mass, a loss of mass.
Oh,
So think about E equals mc squared.
all of them?
All of them. All nuclear reactions lose mass, all of them. How many of them result in the mass number being lessened?
Just
Alpha.
Just the alpha decay. So it's a little deceptive when we say reduces mass here. It really reduces the mass number more specifically. And the heavy elements want to have their mass number reduced a lot. So notice every nuclear reaction reduces mass, all of them. Only this one actually changes the mass number, though. So you may simply, be given an element, and you may have to simply predict what is the most likely route of decay. If the element has a higher atomic number than 83, then its most likely route of decay is alpha decay. So beyond elements not being higher than 83 atomic number, you'll have to look at the N over Z ratio and just figure out if it's, typically, again, they're going to ask you for atomic numbers less than 20. What's the N over Z ratio supposed to be for atomic numbers less than 20? For 1 for stability. So if it's not equal to 1, you want to find out, is it lower than 1? Is it higher than 1? If it's higher than 1, then you want to just simply do beta decay, electron emission. If it's lower than 1, then you want to do either of these two processes, either positron emission or electron capture. Questions? Okay. Home stretch, guys, home stretch. Let's talk really briefly about radioactive decay. So radioactive decay is always a first order process. It's called the whole chapter on kinetics. You can have reactions that are either zero order, first order, or second order. Every once in a blue moon, you might get some theoretical third order reaction or things like that. But for radioactive decay, it's always a first order process. So what's nice about a first order process is your half-life is a constant. So if you recall, N equals N naught e to the negative KT. So this is your first order integrated rate law. This is how something behaves. So, but again, what's nice is that your half-life is constant. So how many people can do exponentials in their head? Yeah, not going to happen. Again, you got no calculator on this. So they can't ask you to do some complex natural log or exponential function in your head. So what they are going to do, though, is they're going to deal with half-lives. So half-life is the amount of time it takes for half of your sample to decay. For half of your sample to decay. So after one half-life, only half of your sample remains. So if I start with a sample, which which means I start with all of it, 100%. How much would be left after one half-life?
50.
How much would be left after another half-life?
25.
How much would be left after another half-life?
12.5.
So on and so forth. So if I start with all of my sample, what fraction would be left after one half-life?
Okay.
1/2. What half? What fraction would remain after a second half-life?
1/4.
What fraction would remain after a third half-life?
1/8.
Cool. And so on and so forth, going on down the line. They could give you an actual mass of some radioactive nuclide. Like they could tell you start with 64 grams of some radioactive nuclide. So let's say I told you that. Let's say I told you you had so 64 grams of some particular radioactive isotope, some nucleus of some sort. So you start with 64 grams, and I tell you that the half-life is equal to 2 hours. Half-life is equal to 2 hours. Question might be is how much would you have left after 10 hours? How much you got left after 10 hours? Well, how long is a half-life again?
2.
2 hours. In 10 hours, how many half-lives will we go through?
5.
5 half-lives. How much would you have left after one half-life?
1/2.
32.
After the second half-life?
16.
After the third half-life?
8.
After the fourth half-life?
4.
And finally, after the fifth half-life, we'd have 2 grams left. So the questions can be as simple as that. So they can't ask it too complex. This one, I gave you a nice example where you got some exact number. Oftentimes, you'll have to approximate a little bit. Cool. This is really all there is to radioactive decay. So again, they can't make this too difficult because you don't have a calculator. Last topic. Let's talk briefly about nuclear binding energy. So if I told you, Casey, that each one of these lovely dry erase markers weighs 1 ounce. So, and I put them all on the table together. How much would all 4 of these together weigh?
4 ounces.
4 ounces. Sweet. Let's add them all together, right? So, but what if these are not dry erase markers? What if these are 2 protons and 2 neutrons? And I'm trying to make helium. I'm trying to make a helium nucleus. Each one of these weighs 1 atomic mass unit approximately. And I put them all together. And how much should my helium nucleus weigh?
4 atomic mass units.
4 atomic mass units. So it turns out, it's not true though. Whenever you take, we know exactly how much a proton or neutron weighs. Whenever you put them together to form a nucleus, it turns out the nucleus will always weigh a little bit less than the protons and neutrons weighed separately, all by themselves. Where did that mass go? Well, that mass was converted into energy. And it is the energy that is holding that nucleus together. Again, protons don't like each other. They repel each other. And so if you're going to stick protons together in a nucleus, so something's going to have to hold those protons in place. And it's the nuclear binding energy that's holding them into place. So these protons and neutrons get together and they say, okay guys, if we're going to make this work, we don't like each other. If we're going to make this work, we're all going to have to sacrifice a little bit. We have to take a little bit of our mass and use it as the energy that's going to hold us together. So that is this nuclear binding energy. So if you look, you can calculate out that nuclear binding energy with, again, Einstein's lovely equation, E equals mc squared, where here we're going to be using E equals delta m, the change in mass, times c squared. So in that change in mass, that is the mass defect. So that is the difference in the mass between how much the individual protons and neutrons weigh as compared to how much the nucleus weighs. And again, the intact nucleus will always weigh a little bit less than the separate protons and neutrons. And the difference between the two is called the mass defect. So if you take that mass defect and plug it into E equals mc squared, so this mass defect has to be in kilograms for the units to work out properly. So typically you can get some big, ugly, calculation in a standard general chemistry class. So because this mass defect's got to be in kilograms, we typically give you a bunch of data on the protons and neutrons in AMUs. So you got to convert AMUs to kilograms, and it's a big mess. So typically not going to get such a big calculation on something like this. So but there's a couple things you've got to be aware of. This nuclear binding energy can typically be expressed in one of a couple of different ways. So we can look at this nuclear binding energy. We can look at the total. Or we can look at it on a per nucleon basis. So let's say, Alan and Casey, I was going to hire you guys to babysit for me. And I decided to pay Casey $10 an hour. But I decided to pay Alan $20 an hour. Who got the better deal? So you might think it was Alan, but what I didn't tell you is that Casey, I just want you to watch one kid. Alan, I want you to watch 20 kids. So 20 kids for $20 an hour or one kid for $10 an hour, who got the better deal? So you did, because you got $10 an hour per kid, whereas Alan got $1 an hour per kid. So when you look at it on a per kid basis, it's the only really fair way to look at it. And Casey got a much better deal. Same thing with nuclear binding energy. If we just look at the total, like if we just looked at the $20 an hour versus $10 an hour, it seemed like Alan was getting a better deal. So if we just look at the total, it's a little deceptive. But if we look at it per nucleon, now a nucleon is whatever lives in the nucleus, i.e. either a proton or a neutron. So if you look at that, how much energy there is, the total. So, but if you take that and divide it by the total number of protons and neutrons combined, the total number of nucleons, that'll give you a more fair comparison. So if you look, it turns out that iron 56 Iron 56, I'll write it real big here. Iron 56 has the highest nuclear binding energy per nucleon of any element in existence. It is top dog. Nobody's higher. So if you compare him to like uranium-235. Well, uranium-235 is highly, highly reactive, whereas iron 56 is not radioactive at all. But uranium-235 has a much higher total nuclear binding energy. Well, it has more nucleons though. So, but if you take and divide, the total for uranium-235 you divide it by 235, or you take the total for iron and divide it by 56, you'll find that iron is substantially higher on the per nucleon level. So, making it more stable. So if you're trying to, gauge stability and radioactivity, you want to look at the per nucleon basis, which is typically how the question is going to be asked.
So the less per nucleon, the more unstable it is.
Exactly. So the less binding energy per nucleon, the less unstable. The less stable and more likely to be radioactive. Cool. You can often end up doing a calculation on something like this. Sometimes they'll give you the mass defect. And then they're expecting you to compare certain nuclear binding energies. Well, notice the mass defect. The mass defect, you'll always have to multiply it by c squared for anybody. And if you're doing it on a per nucleon basis, just divide by the number of nucleons. So whether you go and try and multiply by 3 times 10 to the 8th meters per second squared, and then divide by the number of nucleons, Or if you just take each of the element's individual mass defects and divide by the number of nucleons, you'll get the same relative scale. So whoever's got the highest mass defect per nucleon will also have the highest nuclear binding energy per nucleon. So don't do more calculations than you have to. So also, it's often really convenient to remember that iron 56 has the highest nuclear binding energy per nucleon. And the closer you are to a mass of 56, typically the higher your nuclear binding energy per nucleon. So it's not proximity on the periodic table, but closeness in terms of having a mass number close to 56. So oftentimes they'll give you 4 nuclei, and they might even give you all the data so that you can calculate all the nuclear binding energies. But if you had a bunch of these nuclei, 4 or 5 for answer choices, and one of them happened to be like chromium 52. Well, chromium 52 is really close to iron 56 in mass. And he's probably going to have the highest nuclear binding energy as a result out of any other choices you might give. So if you got iron 56 as a choice, hey, so much easier. So sometimes you can avoid a calculation altogether. Questions? Questions on anything we've covered tonight? Cool. That's all she wrote.